This paper is titled Audiovisual Segmentation via Unlabeled Frame Exploitation. Audiovisual segmentation, AVS, task aims to segment the sounding objects in video frames with binary masks. Current datasets for the task are usually sparsely annotated. Only few frames in a video frame sequence are annotated with ground truth masks, leaving the rest abundance of frames unlabeled. However, this characteristic is ignored by current methods. And we have done extensive experiments, and the results show that current methods only brings marginal performance gain by using the unlabeled frames, which cause the underutilization of abundant unlabeled frames in the AVS task. To mitigate this and fully unleash the potential of the unlabeled frames, we explicitly divide the unlabeled frames into two categories based on their temporal characteristics, i.e., neighboring frame, NF, and distant frame, DF. NFs, temporally adjacent to the labeled frame, have negligible visual appearance variation of the objects but essential motion information of the objects. And due to the strong association between sound and motion, this motion information is important to the accurate localization of the sounding objects. Contrary to NFs, DFs have long temporal distances from the labeled frame. Though DFs have large visual appearance changes of the objects, but generally share identical semantics. The semantic cues with unlabeled DFs can significantly enrich training data diversity beyond labeled frames, and thereby improve model generalization. Based on the different characteristics of NFs and DFs, we propose different strategies to exploit them. For the former, we extract optical flow and explicitly treat it as model input. The dynamic motion guidance with optical flow is complementary to the static RGB frame input, assisting in accurate sound localization. For the latter, we intend to integrate the DFs into training data, but it has no ground truth supervision. To resolve this, we adopt a teacher-student training network with weak to strong consistency to provide supervision for the unlabeled DFs with the unsupervised consistency loss. The overall algorithm of the proposed framework is illustrated as follows. To verify the effectiveness of the method, we perform experiments based on two representative baseline methods, including TAVI and AV-SegFormer with AVS bench datasets. The quantitative results show that our framework achieves consistent performance gain across all metrics and backbones over the baseline methods. Moreover, compared with prior arts, the model with our methods achieves state-of-the-art performance. As the table shows, for TPAVI, vanilla TPAVI has the worst performance, but by combining with our method, it becomes the second best by outperforming other methods except ours. This quantitative comparison has shown the effectiveness and versatility of our method. In the ablation study, we reveal that both NFs and DFs show notable improvement when applied separately. And when combining the NFs and DFs, the model obtains the best performance across all metrics. And we also present some qualitative results based on TAVI and AV-SegFormer on the two datasets of AVS bench. In this paper, first, we have pointed out the major limitation of previous AVS methods, the underutilization of the abundant unlabeled frames. Second, we proposed a partition strategy to divide the abundant unlabeled frames into two categories, neighboring frame, NF, and distant frame, DF. Finally, we developed a unified and effective unlabeled frame exploitation, UFE, framework to harness the two kinds of unlabeled frames based on their unique traits. Thanks.